Welcome to the Deep Dive, the show where we take your source material and distill it into the essential knowledge you need to be truly well-informed. Today we're diving deep into the cutting edge of large language models, or LLMs, a space that, well, it feels like it reinvents itself every few months.
It really does. And our source material today centers on a truly fascinating new learning paradigm. It's called chain of model, or COM for short.
COM, okay.
Yeah. And it's a concept that promises to maybe revolutionize how we build, scale, and even think about powerful AI.
Sounds significant. So our mission for this deep dive, then, is to explore how COM directly addresses some of the biggest, most stubborn challenges in AI today. Things like the just astronomical cost of training these massive models and critical need for more flexible, adaptable AI.
Exactly.
You're going to walk away with a crystal clear understanding of why this isn't just a tweak, but maybe a significant leap forward in the world of AI.
Let's hope so.
So let's set the stage a bit. LLMs are, frankly, everywhere, and they just keep getting bigger and bigger. But this relentless growth in parameters, it comes with massive training costs and often a surprising lack of flexibility once they're actually built. What are the core problems COM really aims to crack here?
You've hit on the two critical pain points. Current LLM scaling strategies often demand that you train a whole new model from scratch every single time you want a bigger, more capable version.
Right, which seems crazy inefficient.
It's incredibly inefficient and, completely unlike how humans or, well, biological systems incrementally learn and build on existing knowledge.
Yeah.
The other issue is how existing architectures, whether they're dense models or even the more sophisticated ones like mixture of experts, they typically activate a fixed set of parameters. They just lack that dynamic adaptation needed to truly tailor their problem-solving approach to different tasks.
Okay, so COM steps in to tackle these inefficiencies and these kind of rigidities head on. But how does it actually work? When we talk about this chain concept, where does it even start?
It all starts at the most fundamental level, really, with something called chain of representation, or CORE.
Core.
Yeah, imagine any complex piece of information within a model, like a hidden state, which is essentially the model's internal understanding of something at some point.
Okay.
Carr proposes that this isn't just a single monolithic block. Instead, it can always be broken down, seen as a combination of multiple smaller sub-representations, and these are the chains.
Ah, okay. Like nested concepts.
Exactly. Think of it like a set of nested Russian dolls, maybe. Each doll inside provides a more basic core understanding, and as you add more dolls, you get a richer, more detailed picture.
I like that analogy.
So by activating different numbers of these preceding chains, these earlier dolls, you can encode information at varying scales or levels of complexity, all within that single representation. If you only activate the first doll, the smallest one, it's just like a standard representation.
Okay, that makes sense. But here's where it gets really clever, I imagine. Connecting these individual dolls or chains together. How do these sub-representations interact as the information moves through the model's different layers?
That's precisely where chain of layer, or CO, comes into play.
So got it.
COHEL incorporates a really crucial causal relationship. In each layer of the model, any output chain can only see or be conditioned on information from its own input chain and all the input chains that came before it.
Ah, so it builds progressively. Like you can't skip levels.
Exactly. Imagine building a pyramid of knowledge, right? Each new block you add can only be supported by the blocks directly below it and all the ones that came before those. It's inherently ordered.
Okay.
And this design gives us three really fundamental properties. First, generality. Any standard network layer you'd find in a traditional AI model, well, it can actually be thought of as a COHEL with just one chain.
So it's backwards compatible in a sense.
In a sense, yes. It means you can gradually increase a layer's capacity by simply adding more chains without fundamentally changing its architecture. Second, causality. Because of that pyramid-like structure, to compute the features for a specific scale or a specific chain, you only need to activate and compute the parameters associated with that chain and all its preceding ones.
Right, you don't need the bigger chains to compute the smaller ones.
Precisely. This allows for dynamic computation at varying scales, and crucially, it helps avoid catastrophic forgetting.
The classic problem. Forgetting old tricks when learning new ones.
Exactly. The AI equivalent of forgetting where you parked your car after learning, I don't know, quantum physics.
Okay. And the third property?
Compositionality. If you stack multiple layers that all adhere to this call principle, their combined output also naturally maintains this causal chain property. It's like Lego blocks, they just fit together perfectly and the structure holds.
So if Kyle applies to individual layers, giving them this incredible nested cumulative power,
Mm.
then Chain of Model COM takes this concept and applies it to the entire model, start to finish.
You got it. That's the core idea.
That sounds like a true paradigm shift.
It really is. A chain of model is defined as a model where every single layer, from the very beginning to the very end, conforms to that COML property.
Wow.
This means the entire model inherits the generality and the causality of COML. It's truly brilliant because it allows a single model to effectively contain multiple submodels of different sizes and capabilities, all built upon and extending from the previous smaller ones.
So you're not training separate models for different sizes.
No, you're training one model that inherently contains a whole family of models within it.
This sounds incredibly powerful, almost like a unified theory for scalable AI or something.
Yeah.
How does this COMM framework specifically translate into building better, more efficient language models?
Right, the practical application. By applying the COML idea to each layer of the transformer architecture, which, is the backbone of most modern LLM.
Yeah, it's a standard.
We get chain of language model, or CALM.
COLM, okay.
CALM enables what the researchers call multi-scale training, all within a single forward pass in training. Meaning that after training, the model can offer multiple submodels of varying sizes for what they call elastic inference.
Elastic inference, like stretching or shrinking the model as needed.
Pretty much. Adapting its size on the fly to different deployment environments, maybe a small phone or a huge server. It also allows us to scale up models by simply adding more chains, while crucially preserving the capabilities of the previous smaller scales. It's truly incremental learning for these massive models.
That's huge. And then there's column which sounds like it adds another layer of cleverness with something called KV sharing. What exactly is KV sharing, and why is it such a big deal for language models?
Yes, CALM. It's a major innovation, really. In standard attention mechanisms, LLMs generate these things called keys and values the KV cache. Think of them as the model's way of understanding what parts of the input text are important and how important they are for generating the next word or token.
Right, the attention mechanism relies on those.
Exactly. And these KV caches are constantly being computed and recomputed, and they can be very memory intensive, especially with long inputs. CALM simplifies this dramatically. It computes all keys and values only within the first most foundational chain.
Only the first one?
Only the first one, and then it shares them across all subsequent larger chains.
Huh. Okay, what's fascinating here is that the source mentions this might slightly affect performance, like a minor trade-off, perhaps.
It can, yes. There might be a very small dip sometimes.
But it unlocks some truly incredible new functionalities. What are those big benefits?
It really does open things up. The main benefits are twofold, really. First, it enables seamless switching between different LLM scales without needing to recompute those keys and values. That's huge for efficiency if you need to change model size dynamically.
Okay, less redundant computation.
Right. Second, and arguably most important for user experience, it significantly accelerates pre-filling.
Pre-filling, that's processing the initial prompt, right?
Yep.
Before it starts generating.
Exactly. It's when the LLM reads and understands your entire prompt to build that initial KV state. With CALM, since those KVs are computed only in the smallest, first chain, pre-filling becomes dramatically faster.
That's new.
This is genuinely a first in the field, achieving this kind of pre-fill acceleration through architectural design.
Okay, now for the critical question. Does all this theoretical elegance, this clever design, actually translate into real-world advantages?
Yeah.
What did the experiments show? Did it work?
Yeah, the rubber meets the road. The results are pretty compelling. First, just looking at overall performance. The CALM family, both regular CALM and CALM, achieves performance that's comparable to standard transformer models on typical common-sense reasoning benchmarks like HelloSwag and BoolQ.
So no major loss in basic capability.
Exactly. Now, CALM with that KV sharing, as we mentioned, might show a minor dip, often in the range of like 0.2% on some tasks. But the flexibility, and especially the speed it provides, that trade-off usually seems well worth it in practical applications.
That makes sense.
What's interesting, too, is a detail about the chain structure. They found that a configuration with two equal chains, say like 16 units of capacity, often performed better than one with more, smaller chains, like 8, even when the total number of parameters was kept similar.
So maybe fewer, larger steps are better than many tiny ones.
It suggests there might be a kind of sweet spot for designing these chains, yeah.
And that flexibility you mentioned, it really shines in areas like chain expansion. What is that, and how does it change the game for building bigger, better LLMs?
Chain expansion is, well, it's like giving your LLM the ability to grow up rather than having to be completely reborn every time you want it to be smarter.
I like that. Less starting from scratch.
Exactly. You can use an already trained model as your starting point. That becomes your initial chain, and then you incrementally add new chains to it, training only the new parts or fine-tuning lightly.
So it builds on prior knowledge?
Precisely. This is similar to older ideas like progressive network architectures, but applied effectively to modern LLMs. It means you can scale up a model's capacity without that massive cost of training from zero, and crucially, you retain all that valuable prior knowledge.
Did they show this working?
They did. They showed this by expanding TinyLlama v1.1 and also Llama 3.2-1b. They got noticeable performance improvements, about 0.92% gain for TinyLlama and 0.14% for the Llama model, even with relatively limited additional training data and time.
That's impressive.
And you can even freeze that first chain entirely during the expansion training. That preserves its original knowledge perfectly and speeds up the training of the new chains even more.
So you can effectively grow your LLM capabilities over time, much like, we build on our own knowledge through education or experience. That's a huge shift from current methods.
It really is.
Okay, what about elastic inference? You mentioned that earlier.
Right, elastic inference. It's all about having a single model artifact, one trained model, that can adapt its computational size to different deployment needs. Whether you're running it on a tiny edge device with limited power or a massive cloud server.
One model fits all, essentially.
Kind of, yeah. Column integrates these multiple submodels within the one structure. So a single pre-training process can serve all those varying demands later on.
How do they show that?
For instance, they demonstrated that a columnar model they trained with two chains, that 16-16 configuration, could seamlessly be run as a smaller, say, 0.33 billion parameter model by just using chain 1, or it could be run as a larger 0.86 billion parameter model by using both chain 1 and chain 2 together.
All from the same saved weights.
Exactly. It provides this on-demand, flexible scaling from just a single trained model.
That's incredibly practical for developers and businesses, I imagine. Less model management. And you mentioned the pre-filling speed up with Calamare earlier. For anyone who's ever waited for an LLM to churn through a long document before responding, this sounds like a very, very big deal for responsiveness, doesn't it?
Oh, absolutely crucial for user experience. That initial wait can be painful. Pre-filling, again, is when the LLM processes your prompt, your input, to generate those keys and values we talked about, basically understanding your query before it starts generating the answer.
Right.
With Calamare, since all those keys and values are computed only within that smaller first chain, you only need to do the heavy lifting for that first, smaller part of the model. It drastically speeds up the whole pre-fill process.
The faster we're talking.
They showed that for longer contexts, which is where pre-filling really bites, Calamare achieved significant speedups. For example, it was 1.6 times faster for that 16-16 chain setting compared to a similar size baseline of Llama.
Okay.
And it got even better with more chains. For a 8-8-8-8 setup, it was 3.4 times faster when processing 1 million tokens.
3 times faster. That's substantial.
It is. But here's the really mind-blowing part. When they combined Calamare with an existing optimization technique called minference.
Okay, stacking optimization.
Yeah. They achieved up to a 27x speedup for a Llama 3.18b equivalent model, processing 1 million tokens.
27 times.
Yes. Reducing pre-filling time from 19-20 seconds, that's over half an hour, down to just 70.1 seconds.
Wow. That's not just a game changer for speed. It's a productivity multiplier.
Yeah.
It enables things that were just too slow before.
Absolutely. And this also means Calamare is kind of ideal for these newer disaggregated architectures people are building where maybe the pre-filling happens on one set of servers and generation on another. You'd only need the first chain's weights on the pre-filling server, significantly cutting the computational load there.
Incredible. Okay, and finally, there's chain tuning. How does this make the fine-tuning process, which is so vital for adapting models to specific tasks, much more efficient?
Right, fine-tuning. Chain tuning leverages Calm's inherent causality, that ordered structure. It allows you to fine-tune only the latter chains while keeping the initial ones frozen.
So you protect the base knowledge.
Exactly. You keep the foundational understanding intact. This is a powerful optimization for several reasons. It drastically reduces tuning costs because you're touching fewer parameters. It helps prevent that catastrophic forgetting of earlier general knowledge.
Right.
And with column error specifically, the keys and values generated by the fine-tuned later chains can still seamlessly use the KVs from the original frozen first chain. It all just works together.
Did they test this too?
Yep. On the standard GLUE benchmark for language understanding tasks, chain tuning boosted average performance significantly from around 48.46 up to 67.79, and they achieved this by fine-tuning only about 42% of the total model parameters.
Wow, big gains with less work.
Pretty much.
So,
And it's also compatible with other popular efficient fine-tuning methods like LoRa, so you could potentially combine chain tuning with LoRa on the later chains for even greater efficiency.
okay, this calm approach sounds genuinely different. How would you explain the core differences to our listener compared to other scaling methods they might know, like mixture of experts or MOE?
That's a really important distinction to make, yeah, because both MOE and CALM aim to scale models and make them more efficient, but their underlying philosophies are quite different.
How so?
MOE typically creates multiple expert networks within the model. These experts are generally equivalent in their capability or scope, and for any given task or token, only a few of these experts are sparsely activated, usually just one or two.
Right. Pick the best expert for the job.
Kind of, and these experts are often located specifically within the feed-forward network, FFN layers of the transformer. COM, on the other hand, builds a sequence of nested experts, or chains. These chains progress typically from weak or general capability to strong or more specialized capability.
Nested, not parallel.
Exactly. Each COM expert, each chain, inherently contains the capability of all its preceding, weaker experts. Their activation isn't sparse, it's nested and cumulative. If you activate chain 3, you're also using chains 1 and 2.
I see.
And importantly, COM can apply to the full model architecture, attention layers, linear layers, everything, not just specific parts like the FFNs where MOE usually lives.
So it's not really a case of choosing one over the other then. They're described as orthogonal approaches.
Exactly. Orthogonal is a good word. They're designed from different perspectives to solve scaling challenges in different ways. You could potentially even combine them in the future.
How would that work?
Well, you could imagine a COM model where each chain itself is internally structured as a mixture of experts. That might leverage advantages from both paradigms. The possibilities are quite intriguing.
Okay, stepping back then. When would a COM architecture be most beneficial for you? Is it something you'd slap onto any LLM project?
Probably not any project. COM seems best suited for large-scale foundation models. It's really an advanced design choice aimed at optimizing the scaling architecture itself, rather than, say, altering the core backbone network, like switching from a transformer to something else.
It's about how you grow the model.
Precisely. And that first chain is particularly critical in colMR, remember, because it determines the fundamental understanding capability by producing all the keys and values. If your model isn't large enough to really benefit from scaling laws in the first place, or if it lacks the need for broad generalization, COM might be overkill. It's about optimizing the journey to truly massive general-purpose AI.
Right. So given all these advantages, what are the current limitations? Or the ongoing challenges with COM? Where are researchers still pushing?
Good question. The main challenges right now seem to lie in the engineering and infrastructure side of things. While COM offers this incredible flexibility, actually training very, very large COM architectures poses some new hurdles,
Such as?
particularly with tensor parallelism. That's the technique used to distribute the computations of a single large layer across many different processing units, like GPUs.
Okay.
The specific way the chain of linear layer works, for example, can apparently increase communication overhead between these processors in certain distributed training setups. It requires more data shuffling compared to standard layers. Though the paper mentions active optimizations are being developed to alleviate this.
So engineering challenges, but solvable ones, hopefully.
Hopefully, yes. Another point is about model depth versus width. COM seems to excel at extending model width. That means adding more dimensions or complexity to its internal representations within each layer via more chains.
Right.
But trying to apply the chain concept directly to model depth, like having chained layers where layer 5 only sees outputs from layers 1 to 4 in a chained way, currently seems to degrade performance.
Why is that?
The thinking is that the lower level key and value states from early layers just aren't sufficient for abstracting the kind of high level features needed across many, many layers. You need the full context each layer depth.
Interesting. So width works, depth not so much yet.
Right. And optimizing that crucial first chain in column air, making it as efficient and powerful as possible since everything relies on it, that's also a key area for future research.
This really raises a fundamental question, doesn't it? In this relentless pursuit of larger, ever more capable LLMs, how might these chained architectures fundamentally reshape our whole approach to continuous learning and resource optimization in AI? Could this be the key to models that truly self-improve and adapt over their lifetime, not just get replaced?
It's a powerful thought.
And that's our deep dive into chain-of-model learning. From its foundational concepts, these chained representations and layers.
The car and go.
Right. All the way to its pretty impressive real-world benefits in efficiency, flexibility, and especially that prefill speed. It's clear this approach is paving a potentially bold new way for building next-generation language models.
Absolutely. This concept of building incrementally, with capabilities being inherited and then expanded upon, it feels like more than just an optimization. It feels like a genuine paradigm shift.
Yeah.
The idea that a single model can flexibly adapt its size and its knowledge for different tasks, it offers a truly compelling vision for the future of AI development. Less waste, more growth.
It certainly gives you something to mull over, doesn't it?
Yeah.
If models can truly learn and grow more like us, building on previous capabilities rather than just starting fresh every single time, what new possibilities does that unlock for AI beyond what we can even imagine today? We'll see you next time for another Deep Dive.